Hi, everyone. Today I'll be presenting the mathematical foundations of line, which stand for Local Interpretable Model-Agnostic Explanations. This is a powerful technique for explaining black box machine learning models, and my goal is to walk you through the core mathematical concepts behind line and demonstrate how it works using a random forest model on the iris data set. So we have to do two things out of the choices given by Dr. Ben. So I have selected a video and a code markdown. So we'll be using the random forest model on the iris data set to demonstrate line. And by the end of this talk, you will understand how line perturbs input data, assigns weight, and fits a local surrogate model to provide interpretable explanation. Let's begin. Yeah. So why do we need explainability? Before we dive into the math, let us all address the fundamental question. Why do we even need explainability in AI? So modern machine learning models, especially deep learning and ensemble models like random forest, are extremely powerful. However, their decisions are difficult to interpret. In high stakes or field, in critical areas like healthcare, finance, and law, the lack of transparency creates serious concerns. So, take an example. Imagine a doctor using AI for medical diagnosis. How can they trust the decision? How can the patient trust his decision? How can the doctor trust the decision of the AI? If an AI denies a loan, how do we explain that to the applicant? These are real world challenges. So LIME is a technique, is an explainability technique that solves this by providing local explanations. So instead of trying to interpret the entire model, it focuses on explaining one specific prediction at a time. Now let's see how LIME achieves this mathematically. So, what is LIME? LIME, or Local Interpretable Model Agnostic Explanations, is a method that explains a single instance of a machine learning model's prediction. So, the key idea is simple. Instead of trying to understand the entire model, LIME creates a local approximation of the model's behavior around that instance. So, how does that happen? So, it creates perturbed sample, it perturbs the input, creates synthetic examples close to the original, observes how the black box model responds, and then builds an interpretable model such as linear regression or random forest to approximate the decision boundary in that small region. This allows us to understand which features were important for that particular prediction. Yeah. So now we will understand the working behind the line algorithm. So to fully understand how line works mathematically, we will break it down into three major steps. So the first is the perturbation sampling. So it is something that how we generate new data points to analyze the model's decision boundary. Then what we do is that we weigh the perturbed samples. We assign weights to samples based on their proximity to the original instance. So it is how line prioritizes the most relevant samples near the original instance. And then we and then we train a local interpretable model. We call it as a local surrogate model. So it is something that how we learn an interpretable function that explains the model's behavior near the instance of interest. So each of these steps has a strong mathematical foundation, and we will explore them in detail. Yeah, so this is the mathematical formulation of the weighting function. I will talk about it in the upcoming slides as well. So it's just the gist of the formula that we will be talking about. This is the formula of the line algorithm. So over here, I've written a note that the line ensures that samples closer to the original instance get higher importance. So I'll be explaining about it in the upcoming slides. So step one. So we do the perturbation sampling. So why do we need perturb sampling? Since we cannot directly inspect how a complex model makes decisions, we simulate a local region around our point of interest by creating multiple slightly modified versions of it. So mathematically, we define this perturb sample as such: xi dash is equal to x naught plus plus it's a random noise. Actually, it's a random noise drawn from a normal distribution with variance sigma square, and then the xi dash are sample x naught is the original instance and xi dash are the perturbed instances. And I told you earlier that we also add random noise that we draw from a normal distribution with variance sigma square. So once we have these new samples, we send them through the original model FX. That is the output. We send it to the FX to get prediction. So over here, we see that y I dash is equal to f of x dash, right? So this allows us to construct data of perturbed instances and corresponding predictions, which will help us approximate how the model behaves locally. And one more point I want to mention in this is that the key insight is that line creates a local neighborhood of points around x naught so that we can observe how the model reacts to small changes. So in step two, we are weighting the nearby samples. That is, we are weighting the perturbed samples. So not all perturbed samples should have the same importance. Samples that are closer to x naught should be weighted higher than those that are farther away. So over here, we see that the mathematical function of the proximity weighting. So Lime assigns a weight to each sample using exponential kernel function. So over here, I have defined the kernel function. So where we see d of x comma x dash is the distance metric, example Euclidean distance or Euclidean distance or Manhattan distance. And it's the distance between the original and the perturbed sample. And sigma is the kernel width, controlling how quickly weight decreases with distance. So it controls the locality. Smaller sigma means only very close points get higher weight. So while we interpret the weighting function, so this function ensures that samples very close to x naught receive a weight near 1, while those further away receive weights close to 0. If x dash is very close to x naught, then the distance between x and x naught would tend to 0, and this function would tend to 1. That is full weight. We'll get the full weight. And if x dash is far away, then this pi of x, right, this exponential function, this kernel function decays exponentially to 0. So this prevents the explanation from being influenced by distant samples that do not contribute meaningfully to the local model. So as I mentioned earlier, that it is not something that we have to take all the points into consideration. So whichever points are influencing it, only such should be taken into consideration. And the key point that which I want to mention over here is that the weighting function ensures that line focuses only on the decision boundary near x naught, not the entire data set. So then we fit a local surrogate model. Why do we need a surrogate model? Now that we have perturbed samples and their weights, we need to train an interpretable model that mimics the original model's behavior in the local region around x naught. So Lime typically uses a linear model for that step, since linear models are easy to interpret. But in our case, in my example, I've used random forest in the Markdown notebook, which you will see. I've used random forest, so we can use it for any model. So the mathematical formulation is that this is the local model g of x found by minimizing the following weighted least square loss function. Over here, if you see, g is the space of the simple model, and then f of x I dash, they are the predictions of the from the random forest. It is the original model's prediction for the perturbed sample xi dash, and pi of x xi dash is the weight assigned to the xi dash, and g of x is an interpretable model. So example, linear regression or random forest, it can be anything else. So what does this equation signify? So Lime is solving a weighted regression problem where samples close to x naught are given high importance when fitting the local model. So by solving this optimization with the help of Lime, we build a simple model that behaves similarly to the complex model in the local neighborhood around x naught. So in our case, we are applying Lime to the random forest. So we generate perturbations around an iris flower sample, and then random forest classifies each perturbed instance, and then Lime assigns weight to perturbed samples based on proximity. And then after which we train a locally surrogate model. We train a local model that is trained to approximate random forest decision near x naught. So then we'll talk about extracting feature importance. So the mathematical interpretation is that once we fit the local linear model, we analyze its coefficient to understand the feature importance. So this is the equation that is over the g of x is equal to w1 x w1 x1 plus w2 x2 plus till w dxt. So each coefficient represents how much feature for each coefficient w represents how much feature x contributes to the prediction. So if the WI, if the weight is greater than zero, it signifies that the feature increases the probability of the predicted class. And if the weight is less than zero, it signifies that the feature decreases the probability of the predicted class. So in our case, I uh, implemented the line algorithm on the iris data set. So on analyzing one particular instance from the test set, what I found is that I found that petal width greater than 1.80 centimeter had a strong negative impact. It pushed the model away from the predicted class. And petal length 4.25, petal length that is less than 4.25, sorry, the first one is petal width, right? That has strong negative impact. And the second one is petal length. So petal length less than sorry, petal length greater than 4.25 centimeter and less than or equal to 5.10 centimeter had a strong positive impact. It supported the prediction. It had a strong positive impact. So line not only tells which features mattered, but also whether they push the model toward or away from the prediction. So when we talk about advantages of Lime, we see that the Lime is model agnostic. Lime is model agnostic, and it works with any black box model. For example, I told you that whether if you want to work with linear regression or if you want to work with random forest, if you want to work with support vector machines, it works for any model, and Lime can be used for images as well. So that's a very important application of line. And then we talk about feature level explanation. So it shows which feature drives the prediction. So as I already mentioned, we found that uh, petal width had a strong negative impact and petal length had a strong positive impact. We come to know which features are contributing to the prediction, which features are contributing most to the prediction. And it is also a kind of a debugging tool. It helps identify model biases, inconsistencies, and by whenever we use a machine learning to solve a particular problem by using if we use explainability techniques, it would be a matter of improving trust in AI for the stakeholders. It will help the stakeholders understand decisions. So, and then when we talk about the limitations of Lime, it's only local. So explanations may not generalize to the entire model. And then it is sensitive to perturbation strategy. Different methods yield different results. And when you run it differently across different samples, it may yield different results. And it assumes linearity. Sometimes if the data set is non-linear, if the decision boundary is somewhat non-linear, it will find a bit difficult to capture non-linear interactions, and the kernel choice impacts results. The weight functions affects the interpretation. So, in summary, we saw that the line explains AI decisions locally using interpretable models. It's an explainability technique that we used to run it local instances. We used to run it locally, and then we used Lime to analyze the random forest classifier on the iris data set. And Lime helps us understand which features drives prediction, and it's very important because in some cases when we do feature engineering, we might not know which feature is contributing to the prediction of our ML model. So in such scenarios, this will help us figure out that which techniques are yielding the best, which features are yielding most to the model prediction. So, and as I mentioned before, explainability is the talk of the town. It's essential for ethical AI debugging and trust. To improve trust, trust is very important in the field of AI. So, by using such techniques, there are techniques as such integrated gradients, GradCam, which you can do it for images. There is something called SHAP, which is an advanced version, which is somewhat advanced compared to Line. So, there are many as such. So, it's a very good explainability technique. So then these are the references. So you can refer the references to get a very good intuition of the working behind these algorithms. And then thank you. It was a pleasure talking to you.